Assalamualaikum and good day. So this week what we're going to do is we're going to start with chapter 4, which is called as the Fourier series. Let me warn you about chapter 4. So in the final exam, so what happened is that there will be only 3 chapters included. So which is going to be chapter 2, chapter 3 and chapter 4. So this is not going to be the exact percentage, this is like a rough percentage. What happened is that like out of the 100%, so 10% mark will come from chapter 2. So like chapter 3 is going to be like 50% or more, so that's chapter 3 plus transform, and chapter 4 is going to contribute another 40%. If you notice, there is a big percentage for chapter 3 and chapter 4, so meaning that you have to be really good at chapter 3 and chapter 4, so in order to get good grades for your final exam and accumulatively for the whole course. All right. And in terms of the difficulty, for me, chapter 4 is not that hard. As long as you know how to do integration by parts, you should have no problem doing chapter 4 Fourier series. However, you have to be very cautious about the concept. So at the beginning of this chapter, I'm only going to discuss some simple concept that you're going to even wonder why is she explaining all this and such. However, at the end, when we start doing the calculation, we're going to use back every single simple concept that I have explained in 4.2 and 4.1. And if you notice in the teaching plan, so this is how it goes. We have 4.1 is going to be periodic function, and 4.2 is going to be even and odd functions, and neither as well. So what I'm going to do is that I'm going to switch the topic. So instead of starting from 4.1, I'm going to start with even and odd function 4.2, and then only I'm going to start with the periodic function, and then we'll go to 4.3 and 4.4. So do not get confused. Why do I start with 4.2? Because I find that it helps student understanding better when I start with 4.2 compared to the 4.1. Right? So let's start with the introduction. As I mentioned to you before, these are just going to be some very simple stuff, to the point that you would wonder why is she explaining all this? Right? But bear in mind, these are going to be very important concepts that we're going to use later in our calculation. Okay, so the introduction. Okay, first of all, we're going to have a look at the relationship of between integral. So we're going to have a look how does integral actually has a relationship with finding the area between a curve and the horizontal axis. So that will be the region. So we wanted to know what is going to be the area if we have a curve and a horizontal axis. So it's going to be the area bounded by both of them. Okay, let's see here, I have a curve that looks like this. I'm going to call this as a function f of t. So let's say, and let's see that the region that we are going to find is going to be bounded from a value of a, and of course the origin over here is going to be a value of 0, and let's say at the end over here this is going to be until value of b. And now the area that I want to find is going to be this. So it's going to be the area that is positioned between the curve f of t and also the horizontal axis. So this is going to be my curve, and this is the horizontal axis. If you notice, instead of using terms like t-axis or x-axis, so this could actually be anything. It could be an x-axis, it could be a t-axis, but in order to make it more general, so I called it as the horizontal axis instead, because it's not necessarily we are going to use x as the axis, or it's not necessarily it's always going to be t as the axis. So you have to be very careful with those things. Right, so now what I'm going to do is I'm going to figure out what is going to be the area of this region right here. And in order to find the area, all I have to do is I'm going to use integral. So basically the area which is bounded by the curve, so this will be the curve, and this is going to be the horizontal axis. So the area is in between is going to be given by integral. So where is going to be the region? So the minimum value of the region is going to be a, the maximum value is going to be until b, so that is going to be an integral from a until b of the function of the curve. So here, so the curve is given by a function f of t, so that is why my integral is going to be from a to b of the function f of t dt. And of course, if you were to integrate the function f of t and then you substitute the lower and also the upper limit, what happened is that you will get what is going to be the area bounded by the curve and the horizontal axis, which is represented by this right here for our case now. Okay, So that will be the relationship. So now I want you to bear in mind that when we integrate, actually what we do is we are finding the area. Okay, let's proceed to the next concept. Okay, so let's suppose I have two regions. Okay, so this is going to be the first region. I'm going to call this as being region A, and this is my second region. I'm going to call this as being region B. So let's see, this is my region A and this is my region B, and let's suppose here this is going to be a value of A, 0 until B. And of course, like if I want to know what is going to be the area of A, so all I have to do is I'm going to integrate. So what is going to be the lowest value? It's going to be from A. So where does it stop? It stops at value of 0. So it's going to be a value from A until 0. So let's say A is given by a function f of t and B is given by function g of t. So that is why when I wanted to know what is going to be the area A, the function that I'm going to integrate is going to be the function f of t dt. So it will be a very similar idea for the case of B as well. So when I wanted to know what is going to be the area B, I'm going to integrate from the lowest point, which is 0, until the highest, which is going to be until B. And now the function is given by g of t dt. Okay, however, right, so that will be a difference between A and B. What happened is that, so if I were to find the area of A, I will get a positive value, right? So here I'll get positive value. But if I were to integrate and find the area of B, which is the integration right here, so what happened is that the integration is going to give me a negative value. So basically, if you like, whether you get a positive or negative value, so that is being determined by the position of the region. For A, what happened is that the region is above the horizontal axis. So I put here above the horizontal axis. So where is your horizontal axis? So it's here. This is my horizontal axis. Okay, so if it's positioned above the horizontal axis, automatically the integration is going to give you a positive value. Okay, and the opposite goes for B. So what happened is that, so the region is below the horizontal axis. So automatically, if you were to apply the concept just now, because it's below the horizontal axis, so automatically when you do the integration, you substitute the lower and upper bound. So you will get that the value is going to be a negative value. So that is why when you find an area and you get a negative value, so you know that area is not supposed to be negative, it's because of the region. Alright, so if it's positive, it's positioned above the horizontal axis. If it's negative, we know right away that the region is positioned below the horizontal axis. So that's the key point, above and below. Alright, so that is how. So the area is going to become positive or negative from the integration. Okay, next. So let me introduce another term to you. Not really introduce, this is just a revision. These are things that you already know. Okay, suppose that A and B, so I have two regions A and B, and we see that these two regions are being symmetric. So what does it mean that when we see that two things are symmetric? What does symmetric means? So symmetric means two things. If I say that this thing and that thing is symmetric, meaning that they are the same. So what are being the same? You have to be very clear with that. So first, they have the same shape. This is going to be the most obvious one. So the shape is exactly the same. And as the shape are exactly the same, so of course the size is also going to be the same. So basically when I see that two things are symmetric, so it means both of this, so that they have the same shape and they also have the same size. Okay, let me sketch this. Right, so let's say I have two regions. Okay, so this is going to be my A region and this is going to be my B region. And of course now we're going to apply this concept. So the fact that my A and my B region, they are symmetric. Of course, when you have a look at my sketching, it doesn't look exactly the same size, but yeah, it's because of my drawing. Okay, but now imagine that A and B, they are actually symmetric. They have the same shape and they have exactly the same size. Okay, let me put this region in purple and the other region, let's put this in green. Okay, and of course, if I wanted to know what is going to be the region A, so let me put down here. Okay, so my region A is going to be given by, so let's see here, start with A0. Okay, because this is going to be symmetric. If this over here is A0, so let's say this is going to be B, right? So if I want to know what is going to be the area of A, so I'm going to put over here again, this is ft and this is going to be gt on the other side. All I have to do is I'm going to integrate from A until 0 of the function f of t dt. But then again, remember that A and B, they are symmetric. They have the same shape and they also have the same size. When we see that they have the same size, automatically we know that the area is also going to be the same. So therefore, we know that the area A is going to equal area B. So this is going to be equivalent if I were to integrate from 0 to B of the function g of t dt, so which is going to be the area of B, right? So basically, area A and area B, they have the same area. So that is why the value of A is going to equal the value of B. Okay, that is why, for example, so let's say if I want to know what is going to be both of the area, I want to know what is going to be A plus B. So what I can do is I can add up both of the region. I can integrate from 0 until A of the function f of t dt. So this will be the area of A, and integrate from 0 until B of the function g of t dt. So this is going to be the area of B. So when I add them up together, of course, I will get both of the region. However, okay, so that is going to be an easier way. Okay, remember, bear in mind. So, however, A, B are symmetric. So when we say that they are symmetric, they have the same size, right? So instead of having to do two integration, I can actually simplify my integration. So what I can do is, I can write that, oh my god, please stick. I can write that A plus B is going to equal the integral. So instead of like having to integrate, do two integration, and I'm going to integrate one each region individually, I can simply take one of the region. I can integrate simply from A until 0 of the function f of t dt, and this will be the region of A. And of course, if I wanted to find the whole region, which is going to be A plus B, all I have to do is multiply by 2. So when I multiply by 2, because they have the same size, automatically now I will get both A and also B. Or, so that will be the same. If I don't want to integrate the region A, I can also integrate region B, which is going to be from 0 until B of the function g of t dt. So this will be region B. But because I know that region A and B, they are equal, so I simply, when I wanted to find what is A plus B, I simply have to multiply this by 2. So there are two ways of doing this, three ways in fact. So either I can do the long way, which is I'm going to integrate, first find the region A and plus the region B. That is one way. So this second way is I'm going to find region A and multiply that by 2, because I know that A is equal B. Or I can also find what is going to be region B and multiply this by 2. But in terms of calculation, so for me, which one is more favorable, I would pick this one. Okay, first, so this one is definitely not one of the choice, because I have to do the integration twice. Remember, the more you integrate, so the more mistake you are prone to make. You are like more exposed to doing more mistakes, right? So you want to avoid that. So therefore, the first method is not a clever way. So you could either choose number 2 or number 3. Okay, however, the risk is that for number 2, if you notice, the region A, its position here, this is my A, right? So this is actually a negative value. So if I were to integrate, I'm going to be integrating from a negative value until 0. So that is one thing that we want to avoid as well. So when we substitute the lower and upper limit, so it would be like the chance for you to make mistake is higher when you pick a negative number compared to a positive number. So that is why instead of picking to integrate region A, so I would definitely choose for region B instead, because the value is just 0 and B is a positive value. So that's why when you come across cases like this, So this is going to be the more favorable choice, right? Okay, so that will be the idea. Okay, now let me recap this again. That will be the case when we have two areas that is side by side for which the areas are the same. So instead of like finding area A and area B, so what we can do is we can just integrate either area A or find area B and simply multiply that by 2. So that is what you can do for cases like this. Okay, let's see what if like they are not side by side. And what I mean is, what if we have some like this? So this is going to be my region A, and this is going to be my region B. Again, let's say it's going to be A, 0, and B, and this is still going to be the same idea. So the fact that A and B are symmetric, they still have the same shape, and they still have the same size. So this is my region A, and this is my region B. And of course, if I were to integrate, the idea is going to be the same as previously. So if I wanted to know what is going to be the region A, so let me put ft and gt again as being the functions. So my A will be the integration from A until 0 of the function f of t dt. And for the case of B, so that will be the integral from 0 to B of the function g of t dt. But we know that because they have the same size, okay, so the value of the integral will be the same. So area A is going to equal to area B. So area A is equal area B. So therefore the integral is going to give you the same value, right? So when you integrate both of this, so you will get the same value. So what do I mean by same value? So it's going to be something like this. For example, so if I get that A is going to equal 5, so B is going to equal negative of 5. Of course, the value will be the same, but the sign will be different. A is positioned above the horizontal axis, so the integration is going to give you a positive value. B is positioned below the horizontal axis, and of course when you integrate, the area is going to give you a negative value. So the only difference is that they're going to give you the same magnitude, right? But the only difference will be one is a positive, one is a negative. So that is why when you come across something that looks like this, they have exactly the same shape, but one area is at the top, one area is at the bottom. So if I add both of the area together, A plus B, so this is definitely going to be 0. Why? Because they're going to cancel each other. So one is going to be a value of 5, so the other one is going to be a value of negative 5. Right? The magnitude is the same, but one positive, one negative, automatically the outcome is going to be 0. So that is why when you come across cases that looks like this, so symmetric, one at the top, one at the bottom, so when you add up the area, it is going to be 0. So they cancel each other. Okay, so now, so let's talk about function.